This material has been reproduced and communicated to you by or on behalf of Deakin University in accordance with Section 113P of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further reproduction or communication of this material by you may be the subject of copyright protection under the Act. Do not remove this notice.
Okay, so good morning, everyone. Can you all hear at the back? You are the last one. Okay. If you can't hear, just let me know because otherwise it won't get recorded. So I need to make sure I have to keep this one upright and close. Unfortunately, that one is dead, so someone have put it outside and not put it into the charge properly. Right. So let's get started. So last week we had a look at Bayesian estimation, and we went through a few examples starting from coin toss and also using two different ways of doing estimations to find out one of the parameters of that experiment, which is in that case it's a bias of the coin. We looked at the frequentist method, we looked at the Bayesian method for that one, and also we looked at how the Bayesian method is becoming a better method in terms of giving prediction accuracy or in terms of doing the estimation. And we also looked at the limitations of maximum likelihood estimate, basically the overfitting part. You need to have large data points to actually get a better output in that case. And we also looked at one of the properties where we've seen that the map estimate, which is the mode of the posterior, also become equal to the maximum likelihood estimate when you are using non-informative prior, basically. Okay. So then we looked at some application examples like how can you use these kind of Bayesian estimation techniques to do some sort of a text analysis. So, and also we looked at some general derivations of Gaussian formulas and also the conjugate properties of those. So that's about the Bayesian estimation and about the probability and stuff. So this week and next week, we are not going to talk about the Bayesian part, but we'll be talking about another important aspect of analyzing data, especially in multivariate and categorical. One of the things that we will be, or a couple of things that we'll be looking at in today's lecture is the dimensionality reduction part. Then this week will be dimensional reduction. Next week we will look at some clustering algorithms. And then is that next week or the following week you have the break? I think following week. Eh? Then after that trimester break, we will go through the EM algorithms, expectation maximization algorithms methods. After that, then we go and start the Bayesian networks, okay, the graphical models. So that's things that we are going to learn in the coming weeks. So today, as I said, we'll look at one little different area where we use the dimensionality reduction. So as you know that nowadays there are quite a lot of data that are being collected, and there's no problem collecting the data. The problem is how to analyze the data. One of the issues with large data is you won't be able to run all the algorithms directly on that particular large data because of the hardware limitations, or computationally it's going to be very high. That means it's going to take longer time to make decisions. So nowadays people want to get the decisions quickly. So you might have to do some sort of pre-processing or some sort of techniques to actually, can we reduce the size or mainly the dimension of the data, and then we can do some analysis. So in the first thing when the big data is encountered is you need to use some sort of visualization mechanism to find out what is buried in there, what sort of patterns there are, or what sort of any clustering structure or any other patterns in there. So 2 dimensions, 3 dimensions, it's easy, but beyond that one, it's a problem. So there are few techniques that have been developed to actually do this kind of dimensionality reduction part. Here we are looking at today the principal component analysis and the multidimensional scaling. This principal component analysis is fairly old technique, but very good mathematical background, and also it's pretty useful technique. So we will look at the principal component analysis in the first half of the lecture, and then we will move to the multidimensional scaling. Right, the principal component analysis, how many of you have already heard about principal component analysis? You must have heard before? Okay, good. So for you, it might be a little bit of revision, but there might be some new things that you will be looking at, especially when you are processing with R, okay? Right, so these techniques are mainly used for dimensional reduction, but that is not the only purpose of principal component analysis. We can use it for lossy data compression. So what do you mean by lossy data compression is, if you have a large data, we will be able to compress it and bring it to a small set of data. That would be enough to actually reveal or do some processing on it. We call it lossy because of the reduction in the dimensionality, we might lose some of the information. That's why it is called lossy data compression. Then other technique is the feature extraction. So when you have large number of features, that means large number of columns in the data, you might want to actually select only a few features and do the analysis, because if you try to incorporate all the features, one is the computational problem. The other problem is some of the variables might influence the decision of the others. And also, this is one of the ways of doing the feature extraction under the principle that it's extracting variables based on where the maximum variance is, okay? But there are other methods also available for feature extraction. So this is one of the ways, principal component analysis. Data visualization, obviously. So we want to project the data to the lower dimensions. That's what this does. And then we visualize it through 2 dimensions or 3 dimensions, basically. So there are a couple of definitions for this principal component analysis. If you look at in the books, both are the same, but in a different way it is actually attacking the same problem. So the definition one is basically the orthogonal projection of the data into a lower dimensional space. That lower dimensional space is called the principal subspace, such that the variance of that projected data is maximized. So first thing you need to note is it's called the orthogonal projection. What do you mean by orthogonal? Have you heard about that word before? You must have. Perpendicular. So we are finding axes that are perpendicular to each other. Okay, that's what you mean by orthogonal projection. Into a lower dimensional in a linear space, we are finding in a linear space. Okay, not linear space. PCA is using the linear space basically, such that the variance of the projected data is maximized. So what we do is when we have data, let's consider you have a three-dimensional data. We try to find the axis that actually has or shows the maximum variance or captures the maximum variance of the data. Okay? So that way the data can be visualized pretty easily. You know, it won't go behind one, the data points won't be hidden behind other points. Okay? So this PCA's main objective is to find the axis such that the variance of the projected data is maximum. There's an alternate definition which says linear projection that minimizes the average projection cost, defined as mean square distance between the data points and their projections. So what it does is, the earlier definition says exactly the same thing but in a different way. But here what it says is, you find the axis and you find the projection of those data to that particular axis, and then you measure what is the difference, that's error. If it is closer to the axis, it will be low error. If it is larger distance from the axis, it will be high error. You calculate those errors and then you square it, sum them together, and you try to find the axis that actually have minimum sum of errors. That is called the least square error method. Okay? Right, so let's look at it a little bit detail. So for example, if you consider the two-dimensional data as shown in this diagram with the x1 and x2 as the variable. Let's say we have data points that are denoted using the blue color as shown here. So what the PCA tries to do is, according to the first definition, first it projects the data onto the line. So let's consider this to be the line I am considering, one of the lines, okay, the red line. You project the data. Project the data means from the data point you drop a perpendicular, and on the line you will have that particular data. Basically it's an image. Okay? So that is called the projected data. So for each data point you just project them. So the green dots are the projected data points on that line. Then you calculate the variance of those green points on that line. Okay, so that is the variance value you will get it for this particular line. So let's say this is the line 1 I consider. Then what you do is you try to find another line. Let's say this is another line, and you do the same thing for each data point. So you just project them to that line, and you will get those green light points there, and now you calculate the variance of those data points. Like that, how many lines you can have? There are infinitely many lines you can have there, okay? But you find one line that has the maximum variance of this one. And that is the principal axis, we call it. Okay? So that's what the definition is, and that's what it does. If you look at the second definition, it says the least square. So what the second definition says is, you take the line, yes, then you do the projection of each data point onto the line, and you measure the difference between these two lengths. So let's say this is the error E1, the distance. This is E2, this is E3, this is E4. Then you calculate the square of these distances. These are called the sum of errors. 1 to how many data points? Let's say n data points. So for this line, this is the total error that you are getting. Similarly, you do it for the another line, do the projection and calculate the error, the sum of scarce errors. And then you find the line that has the minimum of those errors. And from this geometry, you can see that both are giving the same answer, basically. Okay? Right. So let's see how this is basically done. We have seen that how do you find the first line, the first principal component that has the maximum variance. Then how do you find the other one? So the definition says it's an orthogonal projection. So the next line that you are going to find will be perpendicular to the first one. And then you find that line which has the maximum variance of the projected data onto that line again. So that second line will capture the rest of the variance, basically. Okay? If you have larger dimensions, then you keep on going like that. The third one will be perpendicular to these two lines, so it will be another third axis coming out of it. Okay? So that is a procedure to actually find out all the principal components. So PC1, PC2, like that. Right, so geometrically it's clear, intuitively it's clear, but how can we do it through an algorithmic way? There's a way to find these principal components using the property of eigenvalues and eigenvectors of the covariance matrix from the data. Let's see how that is related to these eigenvalues, how these principal components are obtained via these particular eigenvalues and eigenvectors. So let's, to do that, let's consider a projection onto a one-dimensional space. Okay. Define the direction of the space to be a d-dimensional vector u1, and let's choose that particular direction to be a unit vector. What do you mean by unit vector? It has a magnitude of 1. Very good. Yeah. So it is a vector. That means it has a direction, but its length is 1. So usually you get the, if you have any vector, you can get the unit vector by just simply doing that. Okay, that particular thing should be equal to 1. So this is the direction we are concerned about. Then let's say we are taking each data point xn. So I will just throw that particular xn data point to be another vector. Okay. Then we project this. So that means we are projecting this one. When we are projecting, we are getting this particular direction, isn't it, as shown? How do you get that direction? If you can remember the projections that you have done with vectors in your previous studies. Yes, it's related to cosine. Very good. So it's basically what you are finding is mod xn cos theta is the projection here. Okay? But this can be easily obtained by using the dot product between the xn and the ui. So can you remember the dot product? What does the dot product equation is? It is mod u1 times mod xn cos of its angle. It's a scalar value. Okay? So if I divide by this mod of u1 here, what you get? You get u1 over mod u1 times xn dot xn equal to mod xn cos theta. So this is the projection. So the projection can be calculated via this. What is this one? This is just a dot product between the data and onto the unit vector of that line. Okay? So that's what it is doing here. Basically, you can find the projection by just finding the dot product. In other words, you can put it as in matrix form u1t, u1 to the power t, that means transpose times xn. Okay? Then what we had to do, now we have projected all the data to the line. Now we need to find out the variance of that projected data. To calculate the variance, what we do? We need to calculate the mean of those data points. Okay? So that data point we can calculate as 1 over n times sigma xn. So those are the projected vectors. Also, we want to calculate the variance. So variance of the projected data vectors are given by 1 over n times sigma u1 xn minus the mean squared. Okay? So this is a standard equation. Instead of you are working on the real data, now you are working on the projected points. So if you expand this one, simply it is u1t su, where s is the covariance or the variance using the original data. Okay? Right. So now we have got the variance parts. To find the PC, it says you need to find the direction which maximizes this particular variance. That means you need to maximize this u1 t s u1. How can you do that? But you have one constraint here. That constraint is it is to be a unit vector. There are a few ways of actually doing this optimization. There is one optimization method which uses something called Lagrangian method. Have you heard anything about Lagrangian method in other places? Okay, if not, don't worry. Just you need to know is there is an optimization method called Lagrangian method which can be used to actually find or optimize this particular part, this particular objective functions and the constraints. So here the objective is to maximize this particular projection with a u, t, s, u subject to this condition where u1, t, u1 equal to 1. So what the Lagrangian does is, it creates a variable called L, Lagrangian, that's why the name came. Then it puts the objective function u1 st, plus it introduces a variable, a scalar variable called lambda, times all the constraints. So in here, I will just erase this part. So in here the constraint is this one. So you can move to the other side and put it to 0 equal to 1 minus u1 t u1. So you can take this and put it as lambda times lambda 1 times that value. Then what it does is it takes this L, the function, and differentiate with respect to ui because we want to find the direction, as well as it differentiates with respect to the variable that is introduced, that is the lambda, scalar that is introduced. Okay? This is a simple differentiation. When you do that and solve the equation, you get this results, which says s times u1 equal to lambda 1 times u1. Is this a familiar equation for you in matrix? When you are studying about eigenvalues, you have seen the exactly same thing. S is the matrix, u1 is the vector, lambda 1 is the scalar, again u1 is a vector. Okay? So we are trying to find out all the lambdas and u1s that satisfy this particular property. And we know that the way to do is it is the eigenvalue, basically, eigenvalue and eigenvector decomposition. So to do that, what we do, we take this S matrix and we do the eigenvalue decomposition. That is why when you are finding the PCA, you find the covariance matrix and then you find the eigenvalues and eigenvectors. Are you clear about why this is happening? Okay, right. So the total variance of this particular projection, or the variance along this projection, you can obtain it as just simply multiplying this particular part, and that is given by the eigenvalue as well. Okay. So by this one, we have found the first principal component. Then what we do, we try to find the other one in an iterative fashion. A similar principle. We find another line which is perpendicular to this one, and you can take it as a U2 and put a condition it has to be perpendicular, and then follow the same principle. Okay. So when you extend it to a multidimensional case, what happens is, it is simply you find the eigenvalues and eigenvectors of the covariance matrix, and you can now select those eigenvectors that have higher eigenvalues as the principal components. Okay. So this is kind of a proof saying why the eigenvalue and eigenvectors are used for the PCA and how it is obtained. So the 4 steps procedure for PCA is you just compute the mean and the covariance from the data. Okay, remember, you are not calculating from the projected data. You are taking the original data, calculate the mean, calculate the covariance, and then do the eigen decomposition. Let's say you have m eigenvectors there, and you select the largest whatever eigenvectors. Let's say you have selected the largest m eigenvectors. Let's say the dimension of the original data is d, which in this case m will be less than or equal to d. Okay. Then you can actually project these data onto these particular PCs, principal components, by just multiplying, use the eigenvectors, which is a D into M matrix, okay, with the weight matrix, basically the eigenvalue. Okay, then you will get all the projections, and then you can, if you choose 2 of them, then you can actually plot it and see them. So if you look at the computational cost of this procedure, you know that eigenvector decomposition is order of d cube. Okay, so it's a fairly computationally expensive one when it comes to really, really large data. Okay, but there are some techniques have been developed to actually do this decomposition in less than d cube complexity as well. If you are interested, you can go and have a look at some of the papers that actually talks about this. Okay. So in this particular PCA procedure, which involves eigenvalue procedure, what are the main assumptions that are done here? This is working on a distance, and it is using some sort of a Euclidean-based distance between the points. Okay? And another assumption is, as I said, it assumes linear projection. Okay? So the variables are linear related. That's what it assumes. So there should be a linear relationship between variables, and it works on the points, or if you can calculate the distance between them using some sort of a numeric scale, like Euclidean distance or some other scale. If you have ordered data, that means ordinal data, which is not a numeric data, that means you won't be able to use this PCA method. So that means for categorical data, you can't use it. So you can use it for categorical data or ordered data. You can't use it for linear relationship if the linear relationship between the variables is not there. So are there any other techniques that can be used? Yes, that is where we come to the next called the multidimensional scaling. Okay? So that is introduced to actually address these shortcomings. Right, so before going to MDS, we will now go and look at one example data set. From the R library itself you can get it or you can download it. So before starting that, any questions on this PCA? Fairly okay? Good. Right. So this data set is called the US arrest data set. It's basically a violent crime rates by US state. It listing several of those states in the US, and also it gives a number of murders, assault, and also some other values such as urban population and rape that have happened in that particular area. So it's a 4-dimensional data in this case. So this is a fairly old data where it uses 50 US states obviously and 1973. If you look at this data set, the range of values for each and every variable here, you can see that murder is in tens and 9 in 1 digit and 2 digits, assault it in hundreds and 50s and 200s and something like that. The urban population is in 58, 48, 68 in that digit order. The rape is in terms of decimal places, 21, 30, 44, 25, something like that. So you can see there are different ranges and different magnitudes for different variables here. Okay. So when you are doing the principal component analysis, if the data variables have large variance like that, one of them is in tens and another one is in thousands or hundreds or 200, something like that, it's better to actually standardize them or normalize them. Okay? It is not a must, but it is better to do that if it really, the variable values are really, really different. Once you can get this particular data loaded into the R space, you can just call one command, prcomp, with the dataset name or the fields, whatever that you want to do it, and then you can put a parameter called scale. So fortunately, the prcomp already have the scaling parameter. If you set it to true, it will automatically scale all the variables to 0 to 1 or to the range using mean and standard deviation technique. So what is a mean and standard deviation technique? You take each data point, let's say you take one of the variables and find the mean value and the standard deviation of those, and then each data point value will be subtracted from the mean and divided by the standard deviation. Okay, so when you put it true, then it will do the scaling automatically. And then it will do the principal component analysis. So the code is given there so you can run it and see it. The important thing for you is how to interpret these outputs. Okay? So in the exams, you won't be writing any code or anything, as you won't be having any computer there, but you should know how you interpret the R outputs. Okay? So we'll look at some of them. So one of the things very useful in analyzing the principal component is finding out how many dimensions we can choose from the larger dimensions. And we try to choose the dimensions that captures most of the variance. Okay? So one way to do that one is basically when you run this particular prcomp, I will go to the next slide, you will get results like shown here. The first one shows the standard deviations. Basically, these are the eigenvalues. Okay? Then the rotation. So rotations means these are the eigenvectors. Principal component 1, principal component 2, principal component 3, principal component 4. Okay, so remember the PCA is basically doing the rotation and projection, that's all. So when you look at another output that you can see, by simply putting summary and you just put the results that is coming out of this PRCom, it will give you the standard deviations for each principal component. So standard deviation for each principal component means you can calculate the variance, it just square it. Okay? So it shows how much of the variance is captured by each component. Also, it gives you the proportion of the variance calculated. So what it does is it just adds all of the standard deviation squares and then divide by that and then multiply by 100, or here it's in decimal place. So what this one shows is 0.621. That means the first principal component, PC1, is capturing 62% of the variance on the data. Okay. The PC2 is giving 0.24. That means 24% of the variance is captured by the PC2. So like that, it gives you how much percentage of variance is captured. And from this one itself, you can easily see that first two components are capturing fairly high number of variance. If you look at the third one, which is a cumulative proportion, it's simply adding this one together. So it's 0.62 for the first one. The second one is 0.62 plus 0.2474, that is 0.86. Then the next one is 0.86 plus this third component, like that. So you can see that by the second principal component, we have captured already 87% of the variance. Okay? Or the rest, PC3 and PC4, are its very small percentages. So for this one, for dimensional reduction, so from the 4 dimensions, we can reduce it to 2 dimensions and do the analysis, because it has already captured the 86% of the variance. So this information, we can plot it as shown here. So the vertical axis is the variance, and here it's for each principal component. Here we have shown 2 plots. The first plot is the variance or principal components variance obtained by not scaling the data. The second one we obtained after scaling the data. So in this data, you can see that if you look at the first plot, you can still see there's a variance is going down, but it is not that clear when it comes to small variances here. But if you look at the second plot, you can easily see that. So the scaling has some effect on that. Okay? So when you have large variations or large deviations and the magnitudes of the values are very large between the variables, it's good to standardize them. Okay? But it is not a must, but it's good to standardize them. So you can try both and then select which is better. So this is just to view the principal components, but in this case we have only 4-dimensional data, so we were able to just draw it like that. But if you have really large dimensions, say 100-dimension data, you won't be able to plot it like this, but you can use this particular plot where you have the variance across PC number that is plot. This is a good plot because if you look at this, you will be able to figure out a knee point in this curve. Knee point means where the curve starts to change its direction sharply. Okay? So the after first 2 components, then it starts to actually change a little bit higher and then coming almost flat. So that is an indication that could be the number of, that is the indication that is giving us where we can stop or where we can find the number of principal components that are capturing majority of the data points. Okay? So it's basically you just look at the slope basically. So in this case, by 2 afterwards, it starts to actually, the slope starts to go almost flat. Here it's a little bit deeper, so that's the knee point, and from the knee point you will be able to figure out how many principal components are there in this case. only large principal components, so in this case 2 of them. Right. Any questions so far on this? It's fairly straightforward. Another interpretation of these results is this. If you look at one of these principal components, you can see for each variable, the murder, assault, urban pop rape, it is giving some values here. Okay? And those values are actually have some meanings. So for example, if you look at for PC1, the assault, it says 0.58. And if the others are 0.53 and the others are pretty low. So these are called the loadings. Okay? So that means this particular, for PC1, the assault is having a higher loading, okay, towards the PC1. If you look at the second one, PC2, you will be able to see there's a minus 0.87, and then after that you will have only 0.41. These plus and minuses are just the direction, okay? So to find out the loadings, okay, how much effect it has onto a particular, what is the variable that have higher effect onto the PC1 or PC2, we look at the magnitude. So if it is positive or negative, it has the positive, it will be in the similar direction, or it is the opposite direction if it is a minus. Okay. So in the PC2, you can see that the most influencing one is the assault again. PC3, you can say the rape is the one higher loading. So like that, you should be able to interpret which one is having the higher loading or scores towards the variables. So in this case, PC2 is influenced by 2 of the variables, urban population and murder, as I said. So it's a 0.87 and 0.41. So that is a useful information to figure out from the principal component loading itself, eigenvectors from itself. Okay. Any questions so far on that, on those two results? So it's a magnitude you look at. So, okay, let me go to the example. So you hear what it says is 0.87, next one is 0.47, next one is 0.18, this is 0.16. So which one is the largest? Okay. So in this case, there are two, majority of them, 0.87 and 0.41 there. So you look at the magnitude. All right. Right. Now another useful plot that you can obtain from R is called the biplot. So you simply call the function biplot and then with the PRComp results. So what the biplot does is, it gives you a plot like this in here. The x-axis is the PC1, y-axis is the PC2. And what it does is, it gives you the points which are using those projected values. So it uses the projected values from the PC1, projected values on PC2, and represent it as a scatter plot on that. So we will be able to see the points there. In this case, all the points are just shown with the state names because that is what it represents. In addition to that, it also shows the vectors of each variable. Okay. So that is an advantage of this particular plot, the biplot. So from this biplot, there are few things we can find out. So if you look at first the variables that are shown in red arrows, these red arrows actually reveal some information like which of the two variables are highly correlated. So that particular correlation is simply given by looking at the angle between those two red vectors. So if the murder and assault are varying very closely, they are correlated. If the angle is small, that means they are correlated. Okay? If the angle is large, it is not. In fact, it's given by the cos theta value of that particular angle. And the cos theta will be high when the theta is small. Okay? So to find out, okay, in this case, rape and assault here, this has this particular value, before that one. So in this case, if you look at the pair of variables, you can see that assault and murder is having the smallest angle. Okay, therefore they are highly correlated. Whereas if you look at the murder and urban population, the angle is very large. Okay, that is the least correlated one. That is one information you can get from this biplot. Another information you can get is which variable is aligned with the principal component. So if you look at the PC1, it is a horizontal axis. So you look at which variable is closer to the horizontal. So in this case, you can see that the assault and rape are closely aligned with the horizontal axis, which is the PC1. Okay? Whereas if you look at the urban population and the murder, that is aligned closely with the vertical axis, which is the PC2. Okay? So that is another information that you can get from that. So which of the variables are aligned with the principal components that you have got? Okay? So which is actually having the more influence in there? That is the second information. The third one is about the points here. Let's consider this particular point that is shown as California here. And you can see that that California data point is closer to this particular vector urban population. So what does that say is that particular California is having the higher value for that urban population in the data. And you can verify it by looking at that particular data point. So here I have shown you what the values are for the California. These are the variables. Murder has 9, assault has 276, urban population has 91, rape got 40. And I said it has the higher value for the urban population. So if I go and look at the summary of the data sets, let's look at for that urban. Let's look at for the urban population. You can see that urban populations, the maximum value is 91. It has the largest value coming there. It need not be the maximum value, but what it says is if the variable or data point is closer to one of the axes, in this case urban pop, that means that particular variable value will be higher for that particular data point. If it is far away from that, then it will be less. So the diagram itself reveals which is having the larger value, which is having the lower value, without actually looking at the data itself. If the data, let's say you are selecting a data point like West Virginia here, and you can see that it is closer to the negative direction of this particular urban population, if I extend it in the other way around. Okay? That shows it is having a very low value on that. Okay? Another point you can look at is, if you look at the Mississippi point, so there are few axes, that is murder is here, urban population in the negative side is there, and also assault and rape is there. So for urban population, if you look at how the values are, you can see that I have shown it here. Murder is 16.5, assault is 256, urban population is 44, rape is 17.1. It's easier if you look at the scaled value. You can see which one has the larger value and which one has the lower value. What do you expect from the particular plot? Which one is to have the larger value and which one is to have the lower value? Somewhat closer to the urban population in the other direction. Okay. With the in this case, it's shown it as positive, and the murder value, assault, that's the murder value. Sorry, murder value is having a 1.9 this direction. This is having the negative direction in the urban population. This is minus 1.4, right? And the next one closest is the assault, which is 1.05, and then the rape. So by just selecting a point, you will be able to see, okay, which one is going to have higher value, which one is going to have lowest value for all the variables. Okay? So there are three important things that you can get from this biplot. One is about the axis, how correlated they are. If the angle between them is very small, they are highly correlated. And then whether a particular point is closer to which axis. And if it is there, then we know that that is going to have the largest value for that particular, not largest, larger value for that particular variable. And also, what is the other information that you get from the plots here? Purpose of having the PCA and doing the plots, what is the purpose? We want to find some patterns in the data. Okay? So in this case, it looks like you have only one single big cluster, but there are few points that are far away here, in general, if you look at it. Okay? So like these, like all in the one cluster, these are like little bit far away. So by using the PCA, we will be able to see any clustering structure in that particular data. Any questions on that, how to interpret and how to do that? So you should know how to interpret these plots, biplots from the data. Yep. Okay. Good question. So if this particular data is governed by 4 variables here: urban population, rape, assault, and murder. If this point is closer to that urban population, means in the data that is going to have, compared to other data points, that value will be higher value. And murder is a little bit far away than that. So it will be having definitely lower value for that particular murder variable value. That's why you have to compare with the summary of the data where it is. Any other questions? All good? All right. Yep. Yeah. Good question. Very good question. So I said that when you are doing, when you are doing some sort of PCA and when you are applying it for like compression, compressive saving or compressive sensing like kind of things, then you will lose some information. Why we lose is, let's say we are taking this particular data, we apply the PCA and select only the 2 principal components to do further analysis. Further analysis means maybe I might train another machine learning algorithms based on only using these 2. So here the important thing is these 2 principal components are capturing out of 100 only 90% around, 87% of the variance. That means there are 20% of them or 10% of them we are losing. Okay, so that means we will be losing some of the values there. How significant is that? Depends on the application, what you are looking at. Okay, so that is why this is called a lossy compression if you are applying it for that particular use. Very good question. Yes, we want to actually, our aim is to have, we have large data and we want to actually throw away some of the data or throw away some of the variables and reduce that dimension such that we can use it for learning. In doing that one, I don't want to blindly throw away some, but I want to find out which of these variables are highly influencing, or can I find another axis that actually captures most of the variance in the data. So the PCA is doing that job. It finds orthogonal axes that are better than the normal variables that you have, but it captures most of the data. So that is the purpose of this part. Does that answer your question? Anything else? All good? Okay. All right. Oh, it's already 12. Okay, so this is a good time to take a break and come back, and then I will start the multidimensional scaling part. Take a 5 minutes break and come back. Yeah. Transform means you haven't scaled, is it? Okay. Yeah. Because what will happen is now, from the original data set, now you have a projected data. Because from the projection, you can figure out all this, but it will be approximate. Okay, so that is the thing. You can. Yes, if you have d dimensions, maximum you will get only d eigenvectors. But out of that one, then you figure out which of them are having higher eigenvalues. Other way around. PC that's the finding. Okay, PCA is finding some orthogonal projections of the data. We want to find out PC1 is having the highest variance. Then I am curious, which of those variables are contributing high towards the PC1? Then you will look at which of these vectors are aligned with the PC1. And you can see that the assault and this one are very closer to the horizontal line because that is the PC1 I have represented. That means the PC1 is mainly influenced by those two vectors. Alternatively, you can look at the eigenvector, you can look at the matrix vector, and that says which ones are actually influencing high. So whenever you are using those PC1 and PC2 computer analysis, then let's say you get some good results, then we know the original data, these two variables are significant because of the PC1, and the PC1 is actually based on some machine learning algorithm.
Just because the variance of murder and assault was
just because of it is capturing the high variance among the whole data. Can you remember we take all the data points and then we project to the particular point. So it is capturing the higher variance axis.
the principal components are with respect to all the.
Yes. So first one will be the maximum, the higher variance. Then the next one will be the rest of the variance. The other one will be the rest of the variance, like that. Come over here. It's easy. Yeah. What you do? What you can see. That is one way of doing it, or you can apply the PCA and check the result. Usually, you need to look at the linear graph. If it is non-linear, you go for linear. 4 variables. If you have 100 variables, it will give you 100. But in the program, it's basically, if you have 1,000 variables, what's the point in putting all 1,000? It will I don't know about PRCom, whether it is putting 1,000 or not. Usually some programs will only put the maximum. In most of the data points, what you see is very large data. When you look at the eigenvalues, only a few of them will have a higher eigenvalue. Later on, it will go very close to zero, very close to zero. So those are actually not giving much information to this particular area. So you can ignore. So that's why we say largest eigenvalues.
So that is the exact use of an eigenvalue. So which is the most important variable? So every variable is not assigned an eigenvalue.
First, it gives the ranks.
Yeah. Okay. Eigenvalue. So the highest eigenvalue is the most important variable. So
That is
PCA calculates it. So eigenvalue is basically summing up your entire variable.
If you sum up that one, it is equal to the total.
Yeah.
So it is giving the variance.
Right.
Yes, but here we are not finding it. It's part of it. In general, so that is because it has a magnitude 1. When you are multiplying, it's easier. Okay. So if you, let's say you have that particular vector like this one and this one, I am concerned about the direction part and how much of it is actually contributing there. So how do you get the direction part? You have a vector of magnitude 10, but I am on the direction only. So you take it. Then it's easy. The rest is just multiplying by a scale. So we get it to that direction now. Now I want to find out how much magnitude. Sorry. It's very convenient. You can, it's mathematically convenient and then simplify it. It's like number 1.
So in PCA first calculates the best axis that captures the variance, and then it calculates the eigenvalue.
No. The eigenvalue eigencomposition is what it is doing. The first thing I have shown is what it actually does when you take the data. So this is what we want to find out. Fortunately, it becomes so nice that if you find the eigenvalues and eigenvectors, for this data, this is the maximum variance line. That will be the PC.
So if you just feed the eigenvalues and eigenvectors into the program, it finds the best line.
It not finds it gives you all the details here. From that one, you can plot these lines. This is what it is. It's a vector on those variables. So if you look at only 2-dimensional data, then you will have only these two. Then you can calculate the gradient and then you can plot a line. So it's a multiple line, it will be a plane. Okay, so if you have one axis already there, okay, and if you have an axis which is not perpendicular but closer to that one, what will happen is it will try to capture the variance already captured on that within this. The closer it goes, it will try to share it together. So that's why we want to get it perpendicular. But then we know that, okay, that will be different. In this case, it will capture the different part. Then other one we want another perpendicular. So that is the optimum one. Maximum variance line, and
So
the next one
variance, the risk is it already captures the ones that are
lower. So if it is minimum variance, then you are going in the opposite direction.
correct.
You are going from the lower species.
So does capturing minimum variance lead to risk of overfitting in some way?
No, it depends on where you are applying. So it depends what you want. So it depends on the problem. Sometimes you might want to find out maybe the useless data point, not contributing to much variance, much change. You don't need to go in that backward direction. You do this one and find out the least.
Okay, so from these four,
Yes.
so you find out instead of the highest, you find out the lowest.
So it is simple. So
That is noise data, that is noise.
Noise contribution in that particular data part.
And covariance matrix, what exactly does a covariance matrix do?
If you have three-dimensional data, you just multiply 3 by 3, that's the covariance. So this is the the variance, think of the matrix. So if you have only one dimensional data, you have two dimensions, you have covariance because you will have variance between each and every dimension. Okay, let's get started. So far we looked at the PCA. How do you get the principal components? You'd be simply using the eigenvalue, eigenvector decomposition. So you take the data, calculate the covariance matrix, and find the eigenvalue and eigenvalues and the eigenvectors of those covariance matrix. Then you find the larger eigenvalues and the corresponding eigenvectors of that one. Those are the principal components basically. Largest one will be the first principal component, the next largest one will be the second principal component, and so on. And you can use the variance versus the principal component plot to actually find out how many principal components are there in the data, which captures most of the variance. And you can use the knee point to actually figure out that. So I'm now using the lapel mic, but it is halfway charged. So if at the back you didn't hear anything, just let me know. Okay, then I will switch back to the other one. Okay. Right. So now there are a few conditions in using PCA. Basically, you need a distance measure, such as Euclidean distance or some measure to actually compute those particular covariance matrices. And it's a linear projection. So you need to look at whether the variables are linearly related. So it works well for those. When these two things are not there, then we have to look for some other mechanisms. So one of the techniques is called multidimensional scaling. So what the multidimensional scaling does is, instead of working on the distance matrix, it actually need only the similarities between the points. So the similarities between the points means, so let's say they have 2 points, I have to say whether they are very similar, giving a value 1, or it's not similar, that means 0. Okay? So I don't care about the actual values of those. So I need only the similarities between. So what are the examples of such things? So for example, this is useful for if things involving categorical variables. So let's say few people are actually doing wine testing. Okay, and they are giving the scores. And then now we are finding how different each person is. Let's say you have only those similarity scores. This person's prediction and the other person's prediction is close by, then they are very similar, or they are really far away, that means they are dissimilar. So you can have a matrix of similarity matrix, which shows, okay, which are similar and which are not similar. If you have only that information, then how can you actually analyze that particular data? So this multidimensional scaling helps in doing that. So it represents the measurements in similarity or dissimilarity among pairs of objects as distances between points in the lower dimension. So what it does is, you have it in the higher dimensional space, and you have this particular two-way kind of table that you can have. It finds the lower dimensional space. Lower dimensions means either 2 dimensions or 3 dimensions when we are using it for visualization purpose. It tries to represent those data using points in the lower dimensions such that those distances are maintained in the lower dimensions. If the points are far away in the higher dimensional space, then in the lower dimensions also, those represented points should be far away. If certain points are closer, then in the lower dimensions also it should appear as closer. So the relative positions will be same in the lower dimensions and the higher dimensions. So how do you find that particular lower dimensional space and the positions of these points such that it reveals those relative distances accurately, or coming very closer to the original similarities of the points? So that is what the MDS is doing. Okay. There are several applications. So one of them is obviously dimensional reduction, because we can project it to the lower dimension and we are finding it. The other one could be, you can analyze some social science stuff like how the taste differs between people, and if you can find out, okay, what sort of group of people have similar tastes and what sort of people have dissimilar tastes once you have the MDS or lower dimensional diagram. Colors, sounds, those are different variables that you can use. In archaeology, one of the examples is similarity of 2 digging sites. So for example, in archaeology, you will be digging a lot of places and you want to find out which of these places, the artifacts that you have found, have very close or similar patterns. So you might be collecting a lot of features of those artifacts, and you can put it together, and you want to figure out, okay, which ones are closer to each other. So that is in archaeology. And obviously social networks, you might want to find out for example, usually social networks, the relationships are expressed in graphs, and you want to find out, okay, which graphs are closer to each other, meaning which communities are similar, which communities are dissimilar, those kind of things. Okay. Let's take an example and do it. Let's say that I have a data about the travel times between different states or different capital cities of the states in Australia. From Melbourne to Sydney, I know how much it takes, travel time, not the distances. And say Sydney to Adelaide, how long it's going to take, like that. And this particular table is giving those travel time between those different states. So capital of those states, so Adelaide, Alice Springs, Brisbane. So Brisbane to Adelaide is 23, it takes 23 hours, something like that. But I don't have the distance information. By using only this information, can I get a map actually showing where these places are? Okay. So what I can do is, this is the similarity matrix basically. What I have is the time information, which is showing, okay, it is very far or very close. And we can use that one to actually get a map just showing the relative positions of these cities. If we feed this one similarity matrix and to the MDS, what we get is this particular map. By looking at that map, is it accurate? What can you say about this? It doesn't know about the distances, it doesn't know about the coordinates of each data point, each cities. Just looking at that similarity matrix, it has put this particular map. So if you look at these places, Melbourne, Canberra, Sydney, and the position of those places, do they make sense? The relative positions, do they make sense? Make sense. Even though the orientation of the map is different, but their relative distances, which cities are closer to which one, which cities are far away from that, are correctly captured. So that is the functionality of this MDS. Okay, it finds out the relative positions and then puts it in the dimensions what you want, 2 dimensions or 3 dimensions. Okay. So the things that you need to be careful is, there will be some rotations there. Okay. The orientation does not have any meaning, but relative positions will have meaning. Okay? It will be in a different orientation, but the relative positions are preserved. Okay? Right, let's see how we can do this. What are the techniques there? In multidimensional scaling, there are 2 techniques called, one is called the metric MDS, and the other one is called the not metric MDS. It differs based on what sort of similarity matrix you are having. So if you have a quantitative data, that means a numeric similarity data, then we call it as metric MDS. Again, you have the 2 different types depending on what sort of techniques it uses. One is a least square and the other one is a classic MDS. So in the least square one, it is used when you have the distance informations are available. Okay. So if you have the data and if you can calculate the distance, that means you can still produce the similarity matrix, isn't it? So if you have the distance information, then you can use that and then produce the similarity matrix, and then you can use the MDS to do it. If you don't have the distances, but if you have only the similarity matrix, then again we can use this. If it is a numerical one, then you can use the least square or classical MDS. So the classical MDS only uses the similarity matrix basically. Okay. The other one is called non-metric. It is for qualitative data. In this case, you don't have any distance or anything, but what you have is the rank of the data. Okay. It says, okay, this one is first, this one is second, this one is third, this one is fourth, this one is fifth, like that. So it's only the rank information you have. You don't have any distance information. Still, we will be able to actually get a map of those particular data positions, basically. Okay? So that is called the non-metric MDS, and in R we use ISO MDS command to get it. Okay, so let's go through these different techniques briefly. So the first one is the metric MDS. So what it does is, okay, in this MDS process, what the algorithm or the process is this. What it does, it takes the similarity matrix it has between, let's say, the different cities. Then you specify the dimension you want to look at. Let's say I want to look at only the 2 dimensions. Then what it does is, if you have 5 cities, it takes 5 positions. It assumes 5 random positions in the 2-dimension data. Okay? And then it calculates the similarity between the pair of points in the 2 dimensions. Then compare with the original similarity and find how far it is differing. So I can take a pair of points in the 2-dimension data, that randomly selected ones, and then I can calculate what is the difference between them. Similarly, I have the similarity matrix original value from the original data. Then you find how far it is differing. Basically, you subtract and find out what's the error in there. Like that, you calculate it for all the pairs. You combine these together, and that is the function. We call it as stress function. Okay? Instead of error, we call it as stress function. And there's optimization method where it finds the point orientation that have the minimum error, lower stress. Okay? So what it does is it start off with the random points, it calculates the stress, and then it figures out through some optimization method, okay, how I can move these points in the 2 dimensions such that the next time I get a lower stress. You repeat this procedure over and over until you get to the lower stress value, and then you stop at that point. And this is an iterative procedure. So that is what's happening in this MDS process. So this is, yep.
Will you find the lower point first?
Yes. Okay. So in this case, if I have 10 cities, in the 2 dimensions, I need to have 10 cities. So I will have 10 arbitrarily selected points in the 2-dimensional space. I will initially start with 10 points and then start calculating the distances, calculating the stress value, and then move those points in a way such that the next stress value goes down. It is using the gradient descent method, basically. And then at optimum pace, it will, after several iterations, you will get a very low stress value. Then that is an indication where you can stop, and then you can produce a map. That particular map is produced like that. Okay, so it is an iterative procedure to actually get there. Clear? The intuition behind the algorithm. Okay, so then depending on how the stress values is defined, the names change. So the metric MDS, we use the Euclidean distance between the points because we know the distance between the points in this case. So we will be able to calculate the distance between the points, so that we can simply calculate. This is the notation for Euclidean distance. So what it does is it seeks, let's say you want to find a predefined dimension, k dimension. You want to find, if you have n data points, that means you want to find n points in the k dimension that actually represent those particular higher dimensional points. Then you wanted to find out the distances between each pair of those random points in the lower dimensions, and then you compare with the corresponding distance similarity that you have in the original data, which you calculated using the Euclidean distance, and you subtract them and you sum them, and that is called the stress value. And you do this one until you find the minimum stress, and you move the points in the plane. Okay? So by looking at this particular stress value, what you can see, this is a squared error. That is why this is also called as least square MDS. Okay, or another name is called Kruskal-Shepard MDS scaling, Kruskal-Shepard scaling, or KS scaling. So this is the author who have find out this particular method. Okay, the dimension is determined by the user basically. So if I want to find points that represent in 2 dimensions, I will say okay 2 dimensions. Then it will find the best possible point locations in that 2 dimensions. Okay. So simple concept. So we are using here the least square. Since we have the distance information, so we will be able to calculate it. The other method is where you don't have the distance measure, but you have the similarity values, but you will be able to calculate those similarity values as well, even if you have the original point values. In there, what it does is, instead of calculating using the Euclidean distance, it calculates the dot product, the similarity value. The dot product means if you take one data point and then dot with other one, then you will get a similarity value. That is called the similarity matrix. Usually, we center the data. What do you mean by center the data is, we just calculate the mean of the data and then subtract from each data point. So what it effectively does is, it shifts the mean of the data to 0 value. That is called centered. Once we centered the data, then we can find the dot product of it, and that dot product value will be the similarity value. So in the MDS procedure, what now it does is, it finds the Z1, Z2, Zn, those points in the lower dimensional space, and then it calculates the dot product. And then it compares with the original value, similarity value, and then that value will be giving us the stress value for that particular orientation. And you find the best positions that minimizes this particular stress value. When you hear about this dot product, you can relate it to the eigenvalues and eigenvectors that we have seen before. Okay? In fact, if the similarities are centered in a product, it is exactly same as the principal component analysis. Because when you have the dot product, it's basically you are calculating the covariance matrix basically. Okay, so it will be same as doing the principal component analysis. Okay. Right. Now we have 2 different ways of calculating the MDS, which is one is metric method. In that one we have the least square, and the other one is the classical. We call this method as classical method. How do you figure out whether the map that we have got is correct or not? In other words, how can you check the goodness of fit? There is one value already giving us the goodness of fit. What is that? The stress value. So in each iteration, we will be able to monitor the stress value, and that will be an indication of goodness of fit. Later, we will look at a graph, which is called the Shepard graph. That is also useful in finding the goodness of fit for the MDS values. So in the R code that you can use is called the CMD scale. So if you supply CMD scale, then it will give you the classical MDS. The previous example with the cities was obtained using this particular classical MDS, because we have given the similarity matrix and it found it through this particular dot product way using the CMD scale, and then it produces the map in the 2 dimensions. Right, so there are a few advantages of this particular classical MDS. One of the advantages is it's optimal for Euclidean input data. As I said, when it comes to the Euclidean distance, and when we are using the dot product, it is coming similar to the PCA basically. So it is becoming optimal because it's coming into the least square sense, minimum least square sense. Okay, and this method is very fast. You can get these outputs pretty quickly because it just calculates the inner products and do that. And the optimization is basically uses the gradient descent method, where it tries to, the next time where the points needs to move is calculated based on the highest gradient basically, or the highest change that occurs when we change from one position to other position. The next one of the disadvantages, this cannot handle rank data because it still need to have the dot product and calculate it. So if you have only the rank information, it cannot handle. So for that one, we have a method which is called the non-metric MDS. So it works purely on the rank data. So what the non-metric MDS does is, it takes the rank data. So it has the ranks like 1, 2, 3, 4, 5, 6, something like that. Again, it tries to find the points in the lower dimension that approximates the relative distances in the higher dimension, or in this case, approximates the exact ranking in the higher dimension space. To do that, the stress function is defined like this. You take the data in the lower dimensions, obviously you calculate the Euclidean distances between them. That's representing the similarity. Here we calculate, because we have the rank data, we calculate what we call as isotonic functions or isotonic regression function. So what do you mean by isotonic regression function is, it is simply this that is shown in this particular graph. Let's say you have all these red points there. If you are fitting a line, the blue one is the best line that is fitted to it. But you can see that the linear line is not the best one for this particular data because it is coming from lower values here and then it is changing and going there. So there's another way of doing that particular regression which is called isotonic one. What it does is, it tries to find the points which is monotonically increasing. Monotonicity means it increases. Then if you find one point, the next point should be the same value or higher. So it finds those points such that those points are increasing monotonically and they are closer to the data as possible. So that particular line we obtain, it is not a line, it's a combination of several lines. So it's either horizontal, vertical, or in an angle. So you can see that these green points are the isotonic regression. And it captures and it tries to go through where the data is, rather than just a simple linear fit. For the rank data, we need to have a function, so we can find the isotonic function that actually represent that particular ordered data. And we use those two and try to minimize between them. This bottom part is just a normalizing constant, just to make the values between 0 and 1. Okay? Right, in here there are two challenges. That means you not only have to find the Z1, Z2 positions, but here you also need to find the F at the same time. So in the optimization, we use, there is a technique called alternative method. So what it does is, in the first step, it fixes one of them and try to optimize the other variable. And then the next step, it uses the results from the previous one and fix the previous variable and approximate the other one, or finds the optimum of the other one. So in this case, in the first step, it will fix the F and minimize over Zi by gradient descent method, similar to what we had done with the metric one. And in the second step, then you use those Zi and keep it as fixed, and you try to find what is the best F that is approximating. And this alternative procedure is repeated several times until you get the lower stress value. And when you reach that, then that will be the correct positions in the lower dimensions. Okay, so Because it's the rank information is involved and it needs a function that is representative of those ranks, there's isotonic function coming there. Because of that part, this particular optimization become much more complex than the metric one. So running this one will take a little bit more time than the first metric. So that is why that one, first metric MDS is very fast, but this one will take a little bit of more time because it's only working on the rank data. Right. Goodness of fit, again you can use the stress value, but one of the plots that is very useful is called the Shepherd plot. What the Shepherd plot does is it's in the horizontal and vertical axis, it puts the dissimilarities that we obtain in the lower dimension space in one of the axes. On the other axis, it puts the original dissimilarity that we have, and then it puts the points on there. So when you put those points, you can see that for each point, it is like a scatter plot. If the fit is very good, what you expect? You expect the points to be very narrow and very compressed and closer to the middle line kind of thing. So to look at what that particular line, here again the red one is the isotonic fit of that line. So if the points are very close to those red lines, then that is a good indication that this has actually achieved a better representation. If it is a not good one, what will happen is you will see that the point starts to deviate higher from those lines. So in this case, if you look at mostly, you have a lot of points at the lower end, and you have a lot of points in the, less points in the higher end. And you can observe that in the lower end, the spread is a little bit higher than the higher end. What does it tell us? Meaning this particular MDS with whatever the dimension that we have used, let's say 2 dimensions, the far away distant points are captured accurately because they are closer at the higher levels. So these are the dissimilarities, right? So that means at the higher levels they are far away points. So those are actually captured very correctly in the lower dimensions, but close by points it has some errors. Okay, that makes sense as well intuitively. All right. Right. So this is a good plot, Shepherd plot, that actually helps us to find out which is good and which is not good. Any questions on that Shepherd plot? Okay, good. Now we'll go and look at one of the real examples. This is from the data Swiss fertility and socioeconomic indicators. It is obtained in 1888, I think after the World War. They have collected data and about 47 French-speaking provinces in Switzerland. It has 6 variables, and the code for MDS is given there. When you do it for 2 dimensions, you get a plot like this shown here. These numbers are indicating the data point. Basically, it's just a label for the data points. The 6th point, 7th point, 8th point, and things like that. So from this plot, what information you can get? I think I already gave that answer before. Can you interpret anything about the axis? You cannot take any meaning out of these axes, okay? Because they have meaning only with the relative positions. Okay? It is not like PCA. PCA has a meaning, higher loading, lower loading, how those values are related. But here we are dealing with only the rank data or the similarity data. So the axes have no meaning. Okay? It's on the relative positions that makes sense. So that means we can use this one to figure out clusters here. Which points are closer, which points are far away. So here you can see there will be 3 clusters in that particular data, or maybe outliers, depending on how you look at the clusters. Okay, this is the Shepherd plot for that particular fit. What you will do if the Shepherd plot is actually not that great? What can you do? You take the data, you specify the dimension to be 2, and you got this particular results. And I want to improve it. What can I do? You increase the dimension. You increase the third dimension and then find the shepherd plot and see whether it is actually giving a sharp, tight plot. Okay? Because if it is only 2 dimensions, if it has high variation, that means 2 dimensions is not enough to calculate that particular orientations accurately. So you need to have higher dimensions. So what you can do, you can start from 2, you can keep on increasing the dimensions until you find a better fit for you. All right? So that is the way that you figure out how many dimensions are there in this particular data. So the MDS can be used for dimensional reduction, and through this particular exercise you will be able to figure out what are the major axes or how many dimensions basically. In PCA the eigenvalues is giving you the value, but here you had to go through this particular process to do it. All right? Right. Some of the drawbacks of this method is coming from the optimization procedure. Because it is using an alternative optimization method, you can see that in optimization means we are trying to find out the minimum or maximum of a particular function. Okay, let's say we are trying to find out this maximum. This is the maximum, we call it as global maximum. This is also a maximum, but we call it as local maximum. Because of this iterative alternative method, sometimes we might end up in one of the local maximums if we are finding the maximum value. Okay? What can we do in that case? Remember, we are starting with a random point, isn't it? So we can repeat this procedure by having different start points and repeating it several times. So we need to run this procedure several iterations by repeating the initial starting point to be different randomly basically. And you can figure out, okay, which one is giving the lowest stress value or which one is giving the better curve for the shepherd plot. Okay? So that is the procedure to actually find out to reach to the global minimum in this case, because we are minimizing the stress value. So that is one of the drawbacks in this case, and obviously computationally intensive because of that procedure. Advantage of that non-metric MDS is it does not change to rescaling or monotonic variable transformation. Why it doesn't say rescaling? Rescaling means you multiply each variable value by some constant number, because it works with the similarity data, so the actual values does not matter. Okay, the important things are working, so I think I can continue. Right. Sorry, what I was talking about? Right, monotonic variable transformation. Okay, scaling. Because we are dealing with the similarity matrix, we look at the relative distance between them, the scale doesn't matter. So scaling. Okay, right. The other one is the monotonic variable transformation. Remember that we are using the isotonic function fitting regression. So it's an increasing function. If we transform a variable through a monotonic increasing function, that means the similarity still will be preserved. Okay, if it is monotonic increasing, that means it's always increasing. If you do a transformation where it comes down and goes up, that means it will alter the data. The dissimilarity values or similarity values will be different. Okay, so it will not change if you have a monotonic transformation of the data. Works even for rank information, so that is a major advantage. You don't need to have the original positions. So difference between MDS and PCA, MDS does not extract components, okay? The axes are meaningless. Okay? Whereas the PCA, the axes have meaning basically, because it has the axis of maximum variance and you will be able to go back and forth. MDS plus can be scaled or rotated or transformed as long as relative distances are maintained, whereas in PCA you have to be very careful on that. Okay, you should not do those things. When to use MDS and PCA, that is fairly straightforward. If you have the equilibrium distance and the linear relationship, go for the PCA. If you don't have that, then come back to MDS. Okay. PCA calculations are much faster. MDA might take a little bit of time depending on whether it's metric or non-metric MDS basically. Okay, this paper will be good. You can have a look at about the MDS, and also the chapters are mentioned here. So you can go through them. Okay, so today we looked at the dimensional reduction methods, 2 of them. In the next week prac, you will go through some of the real data sets and try to see how you can apply different kind of MDS like this and interpret the results basically. You have to do, so look at, okay, how you can interpret the results, okay, which one is closer, which one is far away, and kind of those things. Okay. I will just take one question which is in the prac, so just to give one of the information. So this particular question says, perform MDS analysis on athletics data using the R. So in this case, it is giving the Olympic marathon data basically how long it takes for a person to complete that particular marathon. So by country it is basically giving us. And when you do the MDS plot, it is coming like this. So what can you interpret from that? If you look at these countries, Netherlands, Mauritius, Cook Island, I think, West Samoa, they are a bit far away, meaning they are taking higher time to finish. Is it a good thing or bad thing? Bad thing. So this is you have to look at the context. Okay, so in this case, larger value is not good. So these are not that performing well, and you can see some clusters of countries which are really performing pretty well. So these are the kind of interpretations that you have to make by looking at those plots. Okay. So similarly, there are other questions also that look at different interpretations. So you can go through it during the prac. It's basically the answers have also there, so you can do that. The first question is just to create some data set and create a biplot and see which one is actually aligning with the major PC, in this case with PC1. So it's basically the code will do it, and then you have to interpret the results. Okay. Okay, good. Any questions? All good? Okay, so thank you for coming, and we'll see you next week then.
But it is written that the theta is 0 if you have large square quotient.
Theta is 0, yeah. Okay, it depends. Is it the theta represent the mean?
No. It's like, I don't know why because the theta is 0. I don't understand that. If you have time, I have some questions.
Yep, you can do it. Look at it. Yeah. Let's go out and look at it. So a lot of people can wait for me. Let's go out and talk.
I had that question also, which is and so if you have some
Yep. Yeah, those questions in the end, the answers, I have put the references and chapters number, so you can go and have a look at that.
I check those questions which are in reference.
Okay.
So I have some problem with that.
Yeah. We will discuss now, yeah. At that. Oh, all right.
To give some time.
Okay, you can come in during the consultation, 2 o'clock today.
2 o'clock today.
Yeah. You can come and give me a call from the pod, and I'll come there. Come to the room, it's in the room, E222. So when you come up to level 2 there, you will see an iPad there that you can call. Okay. What's your name? Manish. See you then.